Okay, so vector fields, on one hand, we're studying vector fields, and we'll just continue for a little bit longer, but really we are studying vector fields for a purpose that is much more narrow, and that is for studying functions of several variables. Compare how far we got with the parametric curves. We did both differentiation and integration. That was what calculus is. So calculus parametric curves, we almost know everything to know about it from the point of view of calculus. These are the derivatives. These are integrals or antiderivatives of parametric curves. With a function of several variables, not so much. Well, the only thing that we have spent a lot of time doing, and we know how to, and that's exactly that, Riemann integral. But Riemann integral gives you a number that's not the same as anti-differentiation. In fact, none of the, say, what is function of two variables, the derivative of some other function, and the answer is no. From our table, there is no arrow that comes into this function, or that function for that matter. So there won't be any integration in that sense. So looking for antiderivatives, there are none. Okay, but we know the way the derivatives are, and they are vector fields, and that's why we turn to vector fields, and that's even though, as that sentence at the bottom says, it is not every vector field is the gradient, but ultimately we want to understand vector fields in order to understand gradients, in order to understand the function of several variables. Okay, so this is what we have done. So remember that issue was addressed a couple of times. So one successfully, one unsuccessfully. Finding the gradient of finding the potential function of a vector field. So one example of that source or the flow of down the hill. That is a potential vector. Is a gradient vector field, and it has a potential, and that is the potential function, a function of two variables. With this one, the answer was no, and so that's to be remembered, and still we'll keep coming back to that. That some of the vector fields are not gradients. So they're not gradient vector fields. There is no surface down which water is flowing, producing these arrows. Okay, so this is not a view from above of any kind of surface with the water flowing down it. Okay, so even though you can certainly think of like it looks like a world and maybe like down a drain, but that's just it's not. Well, as you actually know, in the drain, when you go down the drain, it's not that rotation, the source of what creates that rotation. It's not the gravity. The whirl in the drain, in the bathtub, doesn't go like this, it goes like that, almost in the opposite direction like this. So what creates the rotation? Nobody knows? The Coriolis effect, anyone? It is the rotation of the Earth. Yeah. So gravity itself will not create such a pattern unless you sort of push it originally. So you imagine a funnel, and if you start, you imagine a funnel, and suppose water is dripping down it, but it's not going to start rotating around it unless there is some either initial velocity, push it sideways, and then you have a whirl, or there has to be another force, and that force will be, or another cause to make it rotate. Okay, so that's why. So once again, this is not a funnel as you would think. Okay, we had an argument for that, and in addition to the algebras we see have failed here. We'll come back to that. Now, dimension 1, 2, and 3, as well as higher dimensions 2. We know how to compute gradients. The plotting dimensions 3 already hard enough. Dimension 4 in higher we cannot, but the idea still is possible. Remember what we talked about, say maybe 100-dimensional or 1,000-dimensional spaces of space, 100-dimensional space of, say, prices, and then they all progress in a certain direction, and that is once again a vector field. Okay. So now we will look at vector fields in a very kind of superficial, non-calculus way, just see what can happen to it. And the output of a vector field is a vector, which means that whatever we can do with vectors, we can do with vector fields, such as adding vectors, right here, scale multiplication as well. One scale multiplication that I overlooked is actually one of the more interesting one. If you multiply by -1, what happens to the vector? You reverse. And this time, all the vectors of the vector field are reversed. So if we look at those two examples, instead of dripping down, the water will be climbing up the hill. Okay, and or the world will be either going down, it will be going in, or it's going out. So it's total reversal, like this. This is the negative vector. Reverses the orientation, and nothing else. The magnitude is the same. So that's the reversal, negative. Okay, addition is you see here, and now we're turning to to be consistent. We will use vector notation. So we have one example, constant, not the constant vector field, but rather the next one is constant. This one, constant vector field. The previous one is the going away from the origin, whatever that dimension is. And the last one, once again, going away from the origin, but this time we divide by the magnitude, which made every vector a unit vector. With one exception.
Zero.
The zero, and not only it is not a unit vector, but what?
I guess it's not even defined there.
It's not even defined. So in other words, the issue undefined, the issue of the domain remains just as with calculus 1. You're studying a function, always the issue might be what the domain is. And so this is if you try to regularize that vector field, or normalize the word, to make divide the vector by its magnitude. We're making the vector all unit vectors. Looks much better. There is no this explosion, but uniform radial motion. Okay, but then the problem that you create is that the function is undefined, and not only it is undefined, but think about this: is it a removable discontinuity? So removable discontinuity was defined in calculus 1 as a kind of discontinuity which can be removed by assigning a value. So can you think of a value that we assign to 0 so that we will make this vector field continuous, even though we haven't defined continuity, but you can intuitively understand continuity. So think about it for a moment.
I mean, it seems like we'd be able to if the magnitudes of the vectors from all approaches were going to 0, but they're not. They're constant.
They're not there, exactly, yes. So they are the magnitude, so there was no problem until we divided by the magnitude. There was no problem because they're getting shorter and shorter and shorter, and that ensures the continuity. Whichever way you approach the origin, you will end up with 0. So everything is fine. With this, not anymore, because as you approach the origin, the magnitude does not change, and the direction are opposite. So if I take this route, the limit will be this, the same vector, and along any of these lines, the limit vector will be the same, pointing outside, unit non-zero. So once again, different way to approach the origin. Remember the discussion of continuity and limits will give us different answers, and which means that there is no limit, and so there is no limit, no continuity. Okay, so that's certainly a problem. Okay, what else can we do with functions or rather with vector fields? What can we do with vectors? We can do with vector fields as long as domains allows. One thing is, one more operation with vector fields is dot product. So I could do v dot u, which are just two vector fields. So pairwise, and at every location, I will be so that's location. One vector is the vector of v, and the other one of u. And every location they're a different pair, and then we take a dot product of them. The only question is, what is the result of this product?
Scalar.
What?
A scalar, not a vector?
A scalar, yes, but if you just talk about two vectors, if I'm talking about two vector fields, and I take a dot product with them, what do I get? A vector field is a location-dependent vector. Okay, so it's a lot of vectors, one vector at every location. And now we have two of those, and we'll multiply pairwise, so we'll have a number at every location. So in other words,
a surface?
yeah, it's a function of several variables, yes. Yeah, sometimes we do call them scalar functions in order to separate them from vector value functions such as parametric curves of the vector field. So in that way, for example, you can run out, use the dot product, what we know about the dot product, to evaluate the angle between the two vector fields simultaneously at all locations at once. All you have to do is remember the cosine alpha is equal to v dot u over the two magnitudes. Okay, so once again, at zero, if we have a zero vector, that plan fails. Okay, so that would be once again another vector, just a function of several variables. And one more example, what if I take a function of several variables, say I take f of x, y, and I multiply it by a vector field of two variables. So this is vector field, and this is just a function. Okay, so what is the result?
We're changing the magnitude of all the vectors.
Right, so it's a new vector field. Okay, so all of these algebraic operations are possible. If they are possible with vectors, they are possible with vector fields. Okay. So otherwise, they are functions, so they are domains, they are ranges, there are our interpretation. There is also all calculus of vector fields, such as they will have derivatives, they have some kind of integral part. Well, we are talking about how to integrate vector fields exactly producing functions of several variables. That is the subject. Otherwise we are really not looking for the time being at vector fields for their own sakes, but rather for only for the sake of the function of several variables. So to make that point, so let's review that. What we remember, we went over that. So let me put it this way. So the derivative or the derivatives of functions of several variables. How about n variables? N variables are vector fields in Rn, but not vice versa. Okay. Okay. So let's review that part. And go over some properties as well. So we're talking about derivatives of functions of n variables right now, and we are now a little bit familiar with what they are. Okay, so let's review. It is actually about. Yeah, it is about. To begin with, it is let's go the way we did. We start with planes. So planes and lines, because we start with dimension 1. And so as you remember, we have L of x is equal to some p plus m x minus a. Okay, so that's a line. And then we progress to higher dimensions. L of xy is equal to p plus m x minus a plus n y minus b. Okay, now the plane, so that the first one line, this is, the second one is plane. P is once again is just the shift, vertical shift. In the meantime, the point is so it passes through a P, yes, hold on, AP. Okay, so point AP, the plane, it is just a function, a linear function, so the plane or the line is its graph really, but these are linear functions. Functions of several variables. And the graphs are lines, planes, and so on. Okay, so this the first one, line passing by this point slope equation of the line. Okay, so point is AP, M is the slope. Now, secondly, the next one is a function of two variables, and it is passing through the point A, B, P in X, Y, Z plane, and M and N once again are two slopes. The two slopes in the two directions, X and Y. And then we go on with three variables, and you can guess that it progresses on and on with more and more terms. At some point, using vectors is a relief rather than a chore. Okay, rather than trying to understand it, they actually help us to understand things. Okay, so once again, now this time, so it's a function of three variables, and so then what is its graph? Well, it is a four-dimensional plane. Okay, so it is passing through the point in the four-dimensional space, which is A, B, C, P, and M and K are the slopes. Okay, so now if we go to dimension N, dimension 1, 2, 3, N, so you remember what is the linear formula of a linear function, dimension N, point slope formula?
The dot product of this.
That's right, the dot product. So it is, I guess, better if we recognize this as a dot product to begin with. So this is a dot product, and that one is. Okay, in dimension 1, it's dot product is just product. So then we multiply a vector by another vector. M and K is a vector, and the other one is also a vector. So we can circle it. That's one vector, which is made of these slopes, and the other vector is this, which is pretty much like a step away from the initial location, being ABC. Okay, so then we are writing it as L of X. So I'll put X as n-dimensional vector. Okay, and it will be still some P plus mx minus a. A very simple compact formula. So once again, these are the slopes. And a dimensional vector, this is the point in dimension n. So a is 2 in Rn. And so then that makes x minus a is the step from how far you went in what direction away from a. Okay. So that's our formula, and then we move on to functions of general functions of several variables. Then we speak of linear approximations. Linear approximation meaning a linear function. So the definition is so given say what is that? U equal to f of x in Rn, function of n variables. You don't have to think n-dimensional necessarily implies a high dimension. If you're not feel just comfortable with that necessarily, then what you do is you just assume that you can just say to yourself, n is equal to 1, 2, 3. That's it. You don't have to leave the physical space of dimension 3, and then you stay more comfortable. And then whenever you're ready, you progress and start thinking about a high dimension. But the vector notation is still fully applicable, and it gives you this uniform language of handling multiple dimensions at the same time. Okay, so then the linear function, the linear approximation is then L of x, the same function, is equal to p plus mx minus a, is called a linear approximation. Best. the best linear approximation of f at x equal a, if, and we have defined it for a certain limit, which I'm not going to discuss a lot, or at all, but just let's mention it. We are looking at the difference between the two, the function and its approximation divided by the magnitude of our, so the numerator is the error of our approximation, and the denominator is our run. Okay, so once again, error, and this is the run with x approaching a, and it's equal to 0. Okay, and then the theorem that we had, then also under the conditions of the theorem, what is it? M is the gradient of f a. So our function is defined in this indirect way. Well, I guess the second condition is p is equal to f of a. So that point is p has to be specific for our approximation to make sense. So it has to that line or plane has to pass through that point to begin with, the point where the graph passing. Okay, so something like this. It's very much calculus 1 idea. And this is a, and this is p. Okay, and then what is the angle? So point is determined now. What is the angle? And the angle is the gradient, or in dimension 1, it is simply the derivative. Okay, so the gradient of our function is computed then. And we know what it is. It's made of partial derivatives. Okay. So that is the theorem. So we know how to approximate, and and then we treat this and call this the derivative. So let's just say it. This is a vector field. Once taken over all a's. Okay, so the statement of the theorem itself, as well as the definition, is fixed on one particular location. Okay, and so one at a time it is done, and then in that location we say that vector that we're looking for, m, is equal to the gradient of the function at that location. Okay, but if we carry out over the whole domain of the function, then that creates a vector field. Every location, vector field. Okay, so and then I forgot to insert it here. The f is called differential. At x equal a. If it has a linear approximation, and well, if it has linear approximation, then it's called differentiable. And we remember that so these two functions are, in a sense, you can argue that if you go beyond dimension 2, where so dimension 1 line and tangent line, dimension 2 surface tangent plane, dimension 3 already the analogy falls apart. So you can still speak of sort of two functions being tangent to each other in some sense. In what sense? In that sense over there. If you zoom in on a function, remember visualizing functions of three variables is through its surface level surfaces. So if these are level surfaces of f, and suppose there is one point somewhere here, okay? Then what does differentiability mean? If we zoom in, what is going to look like?
Plane.
A bunch of planes. So the level surfaces, which we see a bunch of them at the same around the same location, they both straighten out, and naturally they are parallel, so they cannot possibly cross each other, and even more so, they are kind of at the same, they uniformly distribute, if you like. So I'm not sure if that makes sense. That's roughly what we see. What the differentiability explained in dimension of the fluid. So level surfaces straighten out into planes, and but I cannot point well. And then once they are straightened out, you certainly can see where the gradient is. The gradient is the vector that gives you the plane, right? So once we zoomed in and we can replace the function with a linear function, then we are in this position. All linear functions look like that, and every time this is what we are worried about. That's the vector that gives you the whole plane. Okay, so so properties. So if we're talking about derivatives, we are talking about derivatives. So del f prime of a del or del of f of a, okay, is the derivative. Then we have properties of it. So properties of the derivative. So once again, think calculus 1. Properties of the derivative. Remember any?
We've got other properties, the parallel, the limit laws, the limit properties, like the sum rule.
That's right. So that's how you remember. So every law comes from the law of limits ultimately, but keep keeping a careful eye on what operations are actually possible. So, for example, what operations are not possible is the ones that are not possible with vectors. So we carry out, just talked about minutes ago, about what we can do with vector fields. These are vector fields. Vector fields. Well, actually, I take that back. We are talking about functions of many variables, and they actually, unlike vector fields, have more operations available. So you cannot divide vector fields because you cannot divide vectors. But functions that we are talking about, y equal f of x, this is a real number, and whatever we can do with real numbers, we can do with functions of many variables. So, for example, we can add and subtract, but we can also multiply and divide. So they all will appear. So, but starting with the sum rule naturally. So f plus g prime, f prime plus g prime, or if you, so that you wouldn't think that this is calculus 1. That's the same thing. Different notation, same thing. Sum rule, difference rule, naturally, if you want to have a minuses, doesn't make any difference. The next one is another easy one. The constant multiple rule, right? So CF prime, so you just multiply a function of n variables by constant. And so that C is taken out. And once again, I could do it with the del, with the number notation. Okay, but then still all the rest are there. All the rest are there. So product rule is next. Two functions of several variables can be multiplied. Why? Because the output is a number, so you can do whatever we want. Good news, the formula still works. All formulas still work. So it will be f prime g plus f g prime. Now, they're very innocent looking formula, so what's so special about it that brings us to calculus 3?
We have to redefine what multiplication is.
No, we took care of it today. But if you were thinking about these two, then you're right. What are those?
Primes.
What?
Primes.
No, I mean, those are functions. What kind of functions?
Derivatives.
Yes, they're derivatives of these functions. So what? On that table over here, where are they? these arrows indicate differentiation. So these are vector fields. Okay, so that is the innocent looking formula, look exactly like in calculus 1, but these are vector fields. Okay, in the meantime, f and g are still the same function of two variables, so they're of n variables or whatever. So these are still the same, so just functions. And both in dimension n. So that's why I brought out multiplication of vector fields by function, because that's exactly what's happening. Take a vector field, multiply by a function, which gives me a new vector field. Over here also, vector field multiplied by a function gives me a new vector field. Add two vector fields together, give me a new vector field. Okay? So that's what's hiding behind it, and the primes might be not telling the full story, so that's why putting del is helpful. So that's less likely to be confused with something else like this. So when you see del, you know it's a vector field. And what do you know? The quotient rule also works in exactly the same manner. So f over g prime is equal to f prime g minus g f prime over g. Okay, so no difference whatsoever from calculus 1 formula, and once again you already know how to read the numerator the same way as with the product rule, and so once again combination you have two functions. You have two vector fields, you multiply them together and subtract. And division is okay, once again, this is what is, it's just a number, so there's nothing special about that. And we can divide by numbers, that is also allowed. So that is a short list of 4 main differentiation rules. Which one did I miss?
The chain rule.
The chain rule, right. So that is more complicated, but certainly worthwhile. Remember that whenever you have a function of several variables, it could be, say, x in Rn. There are 2 of them to worry about. So either this from x to r, that is our function, and then you can have either on left or on right, there could be other functions. So well, either say this is h, a function, another just a numerical function. So that's not the least less interesting. So f is a function of several variables, then you can follow it with a function of one variable, and that's a composition, right? So that's one composition. But then you can have it on the other end, precede f by another function. What kind of function is it?
Vector value,
Vector value, yes, vector value. Pick the input. What's the simplest input?
The simplest would just be x.
R is the simplest. X, I'm sorry, why did I put x there? I'm sorry, I think I got variables. I mixed up the, x is the in-dimensional variable, and here I say, what did I do? It's say u, and this is say y. Okay, so these are reals. Real. So I just got confused with the domains versus the actual variable. So here x, n-dimensional location, under f goes to u, which is a real number. That's simply a function of n variables. And then there is a numerical function h, which takes u to 1. Okay. On the left, I pick the simplest of the domains would be r, and I call it t because I want to talk about what?
X being a function of time.
Yes, and so what do we call it?
Parametric.
Right, so this is a parametric group. So if either you follow our function with a function of one variable, that's one composition, the other one is a function of several a vector value function. So remember the metaphor for this the second composition, right? The first, this one. Once again, our function is the terrain. while the, so it gives you altitude at every location. In the meantime, our F is our trip map, I suppose. So we put it is a parameter curve, so at every location, at every moment of time, we know where we're going to be, and so we draw that path. Okay, on a map which is at this point horizontal, like this. So this is our map. We don't know anything else. We just know our coordinates on the surface of the Earth, and we're moving through it maybe like this. Okay, so that's our trip. But the other one is actually has the same thing, but it gives me the level curves. So it's a trip, and if it's hiking trip, then you want to know how high you are, and that's what it is. Remember that these maps are giving you elevation. So every curve represents constant elevation. And so if you, the easiest way then to travel is to follow those curves, and you don't have to climb it. Okay, so then you compose them, and what it gives you instead of location for every time, every moment of time, together it will be elevation or altitude for every time. So in other words, what kind of function is it? Altitude is a number, time is a number, it's just a regular function of one variable. Okay, so, and then we know, if we are progressing to the chain rule, which is the point here, is then we're gonna combine the derivative of this with the derivative of that to produce the derivative of this function. So, well, just I have a moment to guess. So the derivative of a parameter curve we already know. I'm sorry, of a function of several variables. The one on the right, it is the gradient. It's a vector field, right? What is the derivative of a function of, say, a parameter curve in dimension 2? What is it? What's the nature of its derivative?
Wouldn't it technically be the same thing?
Yeah, it is in the same. This is, or rather, over here. This is the derivative becomes vector field. This one becomes still the same kind of function. So this is still a parameter curve. And then remember what the chain rule says. We're supposed to multiply them. How do we multiply a parameter curve by a vector field?
You could take the dot product.
The dot product, yeah. And the number, and the answer is a number, which indeed is the derivative of a function of one variable. So it works out. Vector field, parameter curve, either way, they are vectors, and we multiply them through dot product, and we're producing a number which is the derivative of the resulting function. So everything is just fits together. Okay.